Greetings. Once again, my name is John Gabriel and this is New Calculus Channel. And today I'm going to be continuing on the previous topics and the crisis in mainstream calculus education. So, the previous video I talked about uh, Jeff Nisley and his articles facing the crisis and the crisis in calculus education. Now I'm going to show you one of the videos on the internet. This guy here is called Professor Dave, and he's an idiot, but they're all idiots. All professors of mathematics don't know what they're doing. So in this video here, he's trying to teach the concept of double integrals and show how one can evaluate these, and the fact that a single integral gives you area and a double integral gives you a volume, and he doesn't explain why these things are so. So I'm going to show you in a little while how this works using his example. So when you actually have a function such as this function of two variables, the function of x and y, it's got to be a smooth surface. Okay, it it has to be smooth, and the fact that you're integrating this means that you're automatically using the mean value theorem. Okay, you cannot use the mean value theorem unless the function you're dealing with is smooth. Okay, so it has to be smooth, either a smooth function on a plane or a smooth surface. All right. So what are we thinking about when we're thinking about a smooth surface? So now remember, on a plane, when you have a line like that, the tangent line meets at one point, okay? Just one point, extends to both sides and never crosses it. Now, on a surface, that's different. So if you have a surface like that, okay, then the way you check for tangency is not using a tangent line, but rather a tangent plane, okay? Tangent plane. So you have a tangent plane, and the tangent plane must only touch at one point. It doesn't matter that that plane extends and possibly meets the surface at some other place. That's irrelevant. All we care about is the point of tangency. And of course, this surface here will be smooth if, when we maneuver the plane uh, around any part of the surface, it only touches at one point. And of course, if you look at my book on there are no axioms or postulates in mathematics, you'll see that I define plane in terms of a circle whose radius just increases in all directions. Okay, so that's what the mean value theorem describes in terms of two variables or more. Okay, so let's just clear the surface and go back to Professor Dave and see what he does with these examples. So he gives some weak examples here. He says, let's establish where the boundaries begin. So he first of all sets the boundaries and he begins by saying, okay, let's calculate the integral. And so he gives an example and he gives some useful tips. And finally, but all the while he's doing this, he doesn't understand why you can actually integrate this expression in front of the dy, the dx, and he doesn't have a clue why that is the case. And the clue is that you're applying the mean value theorem. Okay, so not to waste too much time. And also, they gives an example of a triple integral. So now I'm just going to move through to his examples. Okay, so let's look at the first one here. So he says, and I'll do the first one with you, possibly the second one as well. So let's look. Oh, I wanted to show you, but I'll get back to that in a little while. I'll get back to this diagram. So he says something like this. He says, find the double integral from 2 to 3 and 2x to x plus 1 of y plus 3x dx. Okay, so essentially what he's talking about here is that you have to find a function. Okay, when you find the function, it's going to be df or partial df dy, right? Okay, I'm sorry, there was a dy dx here. So it will be a partial df dy for this section. And that turns out to be, I'll tell you now, let's see, turns out to be, if you integrate this with keeping x constant, then you have that over 2 plus 3xy, right? Which you will evaluate between 2x, 2x, and x plus 1 dx. So let's see if we can do this correctly without any errors. And I'm good at making arithmetic mistakes, so you need to check me. So if we substitute x plus 1 in this expression, we'll probably get, let's see, x squared over 2. The middle term is 2x, which divided by 2 is just x. The last term is a half. And then, of course, x. If we put in 2x, we'll get plus 3x squared plus 3x, and that's the first part. Okay, and so this is with the x plus 1. Okay, so I'll put x plus 1 in this expression, and now I'm going to do the 2x. Okay, so the 2x, I hope I've done that right. The 2x is 4x squared over 2 plus 6x squared, like that. And all this with respect, integrate with respect to dx. So a nice way of just getting this done immediately is to get rid of all the same powers. So this is just a half of x squared plus 6 halves minus 4 halves minus 12 halves, and that gives you minus 9 halves, right? So ultimately, you're going to end up with this expression. I think it's going to be, so you got minus 9 halves x squared plus, and you add the x's up. There's 3x plus x, so that's 4x. And the last one, which is just a constant, which is a half. And so what you're going to be doing here now is you're going to be dealing with area, okay? This is area. So area is what when you differentiate this expression here, it's actually a partial derivative. So that will be the same as saying partial delta f over partial delta x. And so we need to integrate this now to get this value, right? So I'm going to, let's see, I'm going to put that on the next screen. So, all right, let's get another screen up here, another free screen. This is this, and we'll say, where is it? Excalibur, like that. Oops, and it doesn't seem to, oh, it's got the same one. That's strange. So can I clear this one? Let's see if I can clear this one and leave the other one alone. Okay, is that like, yep, oh, no, it cleared both. Okay. So now I think what we had was, if I remember correctly, was the integral from 2 to 3, and it was minus 9 halves x squared plus, I think it was 4x plus a half, right? Yeah, I think that's what it was. So if we integrate this, then we'll get, and again, you have to use the mean value theorem here, okay? So always, the reason you can use calculus is because of the mean value theorem. So that's 3 halves if you integrate it, x cubed, right? Plus 2x squared, like that, plus 2x squared, plus x over 2, and you have to evaluate that from 2 to 3. Now, obviously, this here is going to be partial df over partial dx, so that we can get back to this. And if we evaluate it from 3 and 2, then we have to just place 3 in here first. And if we do that, perhaps the easiest way now is to call up another GeoGebra screen and type it in. Let's just do that. That's easier. I can't do that in my head. So let's go over here and let's say delete, and let's say f. Okay, so let's just call this any function f of x equals to minus 3 halves x cubed, like that, plus 2x squared plus x over 2, okay? And that's how the function will look. Not that it matters too much because we're just evaluating. And so we have to evaluate from 2 to 3. So f3 minus f2, right? Okay, so we get minus 18. Now, let's see what he gets. So if we look further on here, oops, there you go. So he did get minus 18 as well. And so that's how you evaluate the volume using two integrals. So first of all, you in the first part, you'd have uh, the the arithmetic mean of the lines times the distance x plus 1 minus 2x. And then the second part, you'd have the area, which you'd average out or take the arithmetic mean of the areas and then multiply it by 1. And that should give you, which is the interval distance, and that should give you minus 18. And it seems like you got the right answer. Okay, so, and this integral here shouldn't be too hard to evaluate either. Let's just do that one quickly. Clear the canvas. Okay, so that integral there is going to be, what is that? That's going to be 0 to 1, 0 to 1, 0 to x plus y. So let's see here if I remember this correctly. It will be 0 to 1, 0 to 1, 0 to x plus y. And then he says x dz dy, x dz dy dx, okay? So then he has x dz dy dx. So again, we apply the mean value theorem here. Leave the first two alone. And then we'll, don't know who that is. I'm not going to answer it. Xz, like that, from 0 to x plus y, dy dx. Okay, so what does that become? So this here becomes x squared plus xy dy dx. And we still have to evaluate that, right? So that's from 0 to 1, 0 to 1. Okay, so if I've done everything right so far, that's going to become, because we need to find the partial dy, partial dy, partial dy dx. Okay, so I'm sorry, partial df dy, which is x squared y plus x y squared over 2 from 0 to 1. I'm just doing this to see if he got the right answer there. I don't see why I shouldn't have, but you never know. So anyway, if we evaluate that, then we'll have the integral from 0 to 1 of x squared, putting that in there. So we don't have to care about the 0 because they're both 0, plus x squared over 2 dx, right? And so this should be reasonably straightforward to integrate, and we get x cubed over 3 plus x squared over 4 from 0 to 1. And we put 1 in there, and it's 1/3 plus 1/4, which if we convert it to 12s, multiplied by 4, that's 4 multiplied by 3. So it looks like it's 7/12, right? And I think that is the answer he got. Okay, so that's how you evaluate for single and double integrals. And of course, nowhere does he mention anything about the mean value theorem because he's an idiot, just like most math professors. And so that's pretty much all I wanted to say. And you can also look at the uh, the 3D functions of f of x plus y. So that was the first one we looked at in the first problem. Okay, that was this one here. And we look at the next one. Why is it? Yeah, this one would have been, I think that was the initial. No, that was the partial df, partial dy. Okay, and of course that would have been evaluated from 2x to x plus 1 with the previous expression. Okay, this one. So that's pretty much all I have to say. Become a subscriber if you're not already a subscriber on my channel, and go to my academia site where you can follow me. Okay, I have a lot of followers already. Go to my profile and you'll see lots of good articles. So you have, first of all, 7 videos. I'm also in the top 0.1%. Actually have 3 books, and so the 3 books are the introduction to the calculus, and then this here is also a book, the non-fictional origins, and so is the ultimate book of numbers. Become a subscriber, tell your friends about it, follow me on academia, and if you're feeling generous, buy me a cup of coffee or a meal at a link which I shall place in the details section. Well, that's all I have to say. I'm John Gabriel. Until next time, this is a new calculus channel. Goodbye.